Okay, so we have breadth first search on graphs, and that lets us find shortest paths from some node to all the nodes in the graph. Let's make it a little more complicated, a little more interesting. In breadth first search, our assumption here with the graph was that every edge had the same length, kind of implicitly, right? Edges have a length. We're just counting the number of steps from one node to another. What's the shortest path, right? But graphs are useful in lots of different domains, applications, as I've been saying. So a very natural thing that's going to happen a lot is that the edges have numbers attached to them. So we want to talk about if it's the most intuitive case that a graph is literally a map of locations and you're trying to get the fastest route from one location to another, the fastest way across town to deliver your food or whatever it is. Then you want to count not just the number of links on the map, but the number of edges on the map, but the length of them, if it's not kind of perfectly to scale. And that kind of makes sense since we're just having this schematic representation of a bunch of points and their connectivity. In a sense, that's what graphs really represent, is the connectivity between nodes, not the distances between them directly until we put numbers on the edge. So we're going to have numbers on the edges for every edge. And we might sometimes just note it as a number on the edge, or we might say the length of UV, because remember, every edge can be defined as UV, 2 points, where the pair of those are in the set of edges. So now a graph is going to be not just the vertices and the edges, but also this lengths function attached to every edge. And we're going to call this a weighted graph, very natural thing to call it. And so the weights could be distances, they could be time, they could be money, they could be energy expended or required, some kind of cost measure. Depends what your nodes are, right? So at the moment, we're going to assume that they're always positive, but later on, we could assume that they're negative. So we're always going to assume that LUV, the edge values are always going to be positive at this point, or 0. We'll allow 0. Okay, so an example, I have one of our undirected graphs here, where we can just say how many connections there are and what the connections are. Just get my initial lines of the graph in. It's almost fully connected. And we'd say we've got some weights on these edges as well. So now we're going to say not just that this is, weight 1, but that these edges have different costs to traverse for whatever meaning of cost. But distance is a good metric for it. Oh, I'm supposed to have one there. One more edge. Okay. Right, so the shortest path in this graph, we want to go, let's say we want to go from 1 to 5, right? What's the distance? So there's lots of different ways to go from 1 to 5, but the shortest path to do it, given the weights of the edges, is via 2, right? So 1 and 2 and 5. And I guess we'd have the length of this, max the length of 1, 2 is 2, the length of 2, 5 is 7, the length of this whole thing is 9, right? And that's the shortest path. So the question is, given a weighted graph, and a start vertex, S, so some particular starting point, how do we find the shortest path from that vertex to every reachable vertex in the graph? And this is analogous to the same reason we're doing that in breadth first search previously, that we're going to go through all the paths in the graph in a nearest order, going by breadth-wise, starting from this node S. But now we want to find the shortest path where they could be weighted. So this adds some complexity to it, but still gives us, still becomes a breadth-first approach. So a really brute force way to do this would be to just use the breadth first search algorithm we have already, convert all of these lengths, so take every length that we have here and turn it into that many edges so that all the edges are evenly weighted. And then we just use our original BFS algorithm, right? So this is a really kind of naive way to do it, but it would have the advantage of we'd know it's correct and we'd know its complexity already. Let's just consider that for a moment, and then we'll come up with a more sensible one, right? So if our original graph was like this, we've just got 3 edges between each of the nodes here, and the weight on it was 2, say, and even this one's 5. Then with this very inefficient new approach, we'd create a node for every one of these lengths so that everything is just a 1. Right, so we got to create 4 nodes here. Now are these real nodes? What do they mean? 1, 2, 3, 4, 5. And implicitly, we're just putting 1 on all these just like we had before. Right? So that should be equivalent to what we had before. Now we have, we went from 3 vertices to 9, but all weight equal to 1, so BFS applies as before. So this isn't a very good algorithm. We know it's going to have the same complexity in the number of vertices and edges as breadth first search, but obviously it's adding a lot of edges to the graph, so it's going to increase that constant even though it's still order the number of edges plus the vertices, which is what we got for BFS before. It's going to be a much larger constant, so that number is going to be bigger. And if the graph is large, it's not going to be very good. And we would waste time traversing edges that really have no meaning, right? So nothing happens until we reach maybe like a real vertex, right? Which is, you know, these ones have been predefined, 1, 2, and 3. And when we're visiting these weird vertices that don't really exist, we have to keep moving, right? So I would say there's also a risk that it's misleading, right? Risky because if we ever forget that what those nodes mean, the intermediary nodes mean, or someone else uses them, they might be interpreted and used some way, when really they're not actually even waypoints. Seems like a bad idea, right? So let's not do this one. What we're going to do is Dijkstra's algorithm. Dijkstra's algorithm is so famous, it gets a fanfare. All right, so what is Dijkstra's algorithm then? Dijkstra's algorithm is just a variation of breadth first search that is going to let us deal with weighted graphs. So what we're solving is the single source shortest path problem. Again, that's a single source S in our graph, and we have some other nodes we want to reach, and we want to find the paths to all of them, but make sure it's the shortest one. There could be other paths, but we want the one that gets us there shortest in consideration of all the weights, whatever that looks like. A caveat here is it's on a positive weighted graph. As we said, we'll have negative weights later, but let's not worry about that right now. So we're going to say that the edges are always positive for all edges. So what we're going to do is maintain an estimate, a new distance to variable, to vertex, which gives you the distance from S to V. But we're going to have an estimate of this at all times. The things we're going to have in this algorithm is that at all times after every loop, we want to ensure that the estimate is never smaller than the true distance, right? So we're going to be maintaining this estimate of distance, and it can be bigger, it's going to be an overestimate, but never an underestimate. And then we're going to keep track of some set of vertices, H, whose distance value may still have to be updated. So remember in breadth first search, we had distance equal to infinity, or distance was final value. Right, we only had those two cases. Now we're going to have a third case, we're going to have something in between, which is indeterminate. Less than infinity, but not quite finished yet. And then we're going to select vertex from this set H that has the smallest distance so far, and we're going to loop through and do more calculations. And we're going to remove it from that set, recalculate its distance to all the vertices that it's connected to, and add those to this set H. So remember in breadth first search, we had the Q data structure. Right? And in Dijkstra, we're going to have a type of queue, we're going to have a priority queue. But this needs to be something where we can store the vertices, the nodes of the graph, and their current estimates of the distance, but that we can remove, at some point here, we have to remove get the vertex that has the current smallest distance estimate. So the nearest one. Of the ones we haven't finished calculating yet, we want to pick the nearest one out on every loop of this algorithm. And so we need a data structure that lets us pick the smallest of a set of elements and that we can add and remove to easily. So the data structure for that, if you need it, is a priority queue. So a priority queue is still a queue like we had before, where elements get added to the back and taken off the front, in the sense that any other things being equal, they'll come out in a first in, first out ordering. But in this case now we also want to have this idea of priority, or as we're using it, distance, some value. Basically any problem where you've got a value that can be attached to every element and you want to sort based on that and have them be pulled out based on that, then the priority queue could be appropriate, right? So maybe you're putting items in and you want to remove the cheapest one or the highest grade or the lowest risk. And even as things get added or removed, the priority, the order that you get sorted on is totally determined by this value. So every element has a numeric key value associated with it, and you want to be able to do these operations. So you need to be able to add elements, reduce the priority, or increase the priority in our case, because we're using distance for an element. So change the priority so that it gets sorted up in a different way. And if it becomes, whichever way you're ordering, if something becomes more important, then it would move up and be returned earlier from this data structure. We'll be able to delete min, so that really is get smallest, right? So this idea of getting the smallest, you want to retrieve it and delete it from the data structure at the same time. And we also get a build one, so given this initial construction of a data structure, given a bunch of elements and their priorities. Them look like more concisely. So we have our Dijkstra algorithm, just like breadth first search, is going to take in a graph and a source point where I can start on the graph, and it's going to grow looking at all the neighbors of that, basically building a tree. In addition, now we have this length function which tells us the positive edge lengths for every edge. And the output's going to be the distance vector from S to U. So like before, we have an init stage where we are going through all the nodes and setting them to infinity, a large distance, and that will be something that we reduce over time. We also have this new previous function that we're setting to basically empty. We'll explain that in a minute. And then for the starting node, we set it to 0. Now, before we initialize the queue to just put that element in the queue, here we have to make a queue from all of the elements we have currently, and we use the distance vector to help us construct it. Now, priority queues can be lots of different structures. We'll talk about that a little bit after, but fundamentally, a lot of them are some kind of tree structured thing where, in our case, the top one would be the S value. We'd say like it's a min priority. So in our case, it's going to be S right away. And then all the other ones are below it. So since all the other ones are infinity, it doesn't really matter where they go as long as they can be found. A min heap will work that way. But there's different structures for doing this. But then we're going to loop through, and every time we go around, we're going to pick something off the queue, the next shortest node, nearest node that we need to fill in, and then we're going to process that. In the priority, in the breadth first search, we removed it directly from the queue, and so we did them in order of all the children of the current node, and then went down. So we knew it was next in the tree that way. But now the next nearest node that we need to explore might be a node further down the tree because the weights in that direction are lower. So that lets essentially, the priority queue lets that basically float to the top so that it can be pulled off as the next element. And that's why it works, really. Once we get the node, we're going to go through all the edges. So that's why we're doing this, the breadth part, where we look at every connected node to this one. But now instead of just updating the distance, we want to figure out if we should basically correct a distance to point there, given some new calculation here. So we can think about this visually. We've got some node that we're looking at, U, that's the current one that we took off, so that's our current candidate that we're investigating all its neighbors, because it's the next closest one for us to visit. And so we know it's got some weight that connects it to one of its neighbors, V. So we think about what happens in the very first case, where S is the only one that has a 0 distance and all the others are infinity. We add, we make the cube, the minimum element is going to be S. We'll take out that element, so U will be S in this case. And we're going to V, which is currently up there. It's our current U. And there's some length on this edge, which is SV. And we want to determine this kind of logic. So we say if the distance to V, which is infinity currently, is greater than distance to U, which is 0, plus that length, then we override it, right? Because that's further. Basically, if your current estimate of the distance this thing is higher than the current one that I can link to you, because I'm at this node, I can get to you V directly now, be one more edge, and so we override it, right? So now the new distance V is just going to become, in this case, the distance for S, which is 0, and the distance between it, which is LSV. So it's just going to become LSV, right? And then we also set this previous link. So previous of V in this case will be set to S, right? So we have a back arrow. This is going to let us construct the paths after we reach nodes by the shortest path, and we've updated the path in that direction as well. Okay, so that's one version of the figure. In the more general case, we're going to be having our root node S, our source node, and we're going to be exploring the tree. We're constructing a tree, but exploring the graph via these neighbors. And at some point, we're going to reach previous nodes. At some point, we're going to reach previous nodes for every node in the graph. In a way, we're always doing that. And there's always kind of one more step that gets us to that one. So we're doing this kind of hopping from nodes to nodes that we have the distances to, and constructing distances that we want to update. So you could say you always sort of know this distance to U, so some node you've reached, and the question then is, which one's bigger, right? Is it better to go, basically V is always, as we're going through and discovering new edges, we find these are the U and V we're always finding are like this, right? And for U, this is known, we know what it is. And for V, we've never calculated it fully because we've never had a direct path there from the source, or it wasn't smaller. And so now we've got a case where we have a path and we say, well, if my distance to U plus this one more arc to V, if that's shortest, the shortest I've seen so far, then I'm going to use that, right? And that becomes the new path, right? But if it's not, then we just keep the old one we have. And remember, initially this is going to be infinity, but it could get updated as you're going around the graph at some point. But then the result of the update then becomes that more directly, what we're really doing is we either leave it to be distance v as it is, or we update it so that the previous v of the previous node of v actually ends up being u, right? So if we're actually using the u root, then this previous node would actually be u, right? Yeah, previous u really is an arc going backwards. Yeah. Previous v. But we only update it if this this calculation works out, and essentially the new route we've discovered via u is better. Once we have it, it allows us to follow them backwards to construct all the paths from S to every node, because as we're going on, we're computing these distances, and that distance doesn't tell you how to get there or which arc was used. It just tells you the running tally score of getting to U somehow from S. So we need these previous links to help us reconstruct that. So what about the runtime for Dijkstra algorithm? It's essentially a breadth first search, so we should imagine that at first glance we should get the same kind of complexity as that. Structurally the algorithm's the same, but we're doing these additional queue operations, so maybe it's going to change. It's going to be slower because of that. So deleting the min, or extracting, get minimum, get highest priority, and remove from data structure, that's going to have an increased complexity. And these insert, decrease key, or increase priority operations. Given looking at the code of the algorithm, we're going to call this delete min, extract min activity once for every vertex, because we have to go to every vertex. It has to get pulled out at some point, so we know we're doing this exactly the same number of times as there are vertices, because once we remove them, we don't put them back in, remember. We also call insert, kind of by symmetry. They all have to be put in there, so make q does v insert operations into this queue, and then we're going to call a decrease key every time we explore an edge. So every time we process one of the edges in the algorithm, we take off the node from it and we increase its priority, so it can now float up higher and be used on a future call to delete min. So every edge has to go through that at some point, because they all start off having, well, the node at the end of them all, the v node, starts off being a distance of infinity, so at some point we have to go over that edge and process it to say that this node now has a realistic value on it. Well, the runtime depends how these are implemented. If we use an array implementation for our priority queue and just kind of calculate all of those scores and kind of resort it in order to delete the min, then we're going to need, every time we process it, we're going to need to go over all the vertices. So it's going to be the same order of complexity as the vertices. Yeah, that's right. So each one of them is going to cost that. The increase insert operation, insert is pretty quick for an array. Because an array we can kind of jump directly to that item. So we have just an array where every element has some score. We could add it, we could change its priority. That'd be easy, but we're searching over the entire array every time to find the minimum. And decrease key would be the same. Decrease key be the same because we can just jump there and change it. And so total runtime will be all of these times how often they're being run. right? So we've got v times of that for the delete min, and then we've got these operations both happening in their own kind of scales. We have to do v inserts and e decrease keys, and so the final complexity is really going to be v squared. It's going to be the dominant thing. Essentially, needing to find those priority, finding the minimum element every time and searching it is really going to dominate, right? So another implementation of a priority queue is a heap. It's a very efficient way to do it. And so is what I was drawing before. You draw a binary tree where it's binary, so they only have two children, left and right. And we don't have a strict ordering, right? So it's not a binary search tree. Because it doesn't say, you know, in a binary search tree, you have a node and the value, all the values on the left node, on the left of the node, are less than all of it, than the parent, and the parent is less than all the children on the right, or the descendants on the right. Right? In a heap, all you say is that the parent nodes are less than the children nodes, if it's a min heap. You could also have a max heap where that's reversed, but for simplicity, we'll say a min heap. And so the child node's value, the parent node, has a value, and all of its descendants on both sides are less than it, greater than it, sorry, greater than it, so it's a min heap. And so the minimum value is always at the root, at the very top of the tree. And you have to have exactly two children, so you have to fill that level before you start the next one across the entire tree. Right? And since the ordering left and right doesn't matter, that means you can make the tree as balanced as possible. Right? It'll be as close to a balance as it can be, so the tree will have similar sides on each left and right. But you do have this ordering that for every node, it's always less than all its children. So it's kind of roughly sorted. And so you know by definition that the root contains a minimum element. And so why do we make a tree like this? I mean, the main reason is because the delete min operation, which is the bottleneck here, that we want to get the lowest distance or highest priority element quickly, that's easy, right? So delete min in this case is order 1, right? Because it's already been computed. Now, obviously, you have to pay for that somewhere. You have to pay for it by having all these various correction calculations, right? So if we insert a new value, we place the value at the bottom of the tree in a leaf, and then we would say bubble it up, not bubble sort, but bubble it up to top until it satisfies the heap property. Right, so you can imagine having a node that's added at the bottom of a tree that exists already. And you'd only have to go up until you reach a node that's less than you. Once you do, you can stop there. It doesn't matter where you are, because left and right are not chosen. It's just that it has to be as balanced as possible. And since it already has this property everywhere else, once you reach a parent that's less than you, you can just stop there and remain their child. Right? So you just swap up and down as you go. So if we think about how much this would cost, at worst case, you'd have to go from the leaf you start at, and we'd pick end of the tree. We want to make it, we'd still have to fill this, each level, satisfy this rule that each level has to be filled before the next level started. So we pick the leaf node at the end that is where the first empty space is on the last level, and add our value there, and we filter up. And so worst case, you'll have to go all the way to the root of the tree. Remember, the root of the tree of a balanced tree is going to be log n, the height of the tree, if it's balanced. Be log n, where n is the number of nodes. Right, so this insert operation could take log of v in our case, if it has to go all the way up to the root. So if we get a new value and it is literally the smallest one that we've ever seen, then it should go up to the top. That should never happen in this case because the root here is the shortest thing. You can't get a shorter path to a new node you've never seen, but it could get quite close. What else do we need? We need the decrease key function. That works the same way as insert. So once we have a node that we've calculated, if we want to decrease its distance, that will increase its priority, we would need to update that vertex's distance value in the tree, and after we update it, we might have to bubble it up and swap it with its parents until it satisfies the heap property again. And again, this will take log v in the worst case. Now we have to go back to this delete min, which I said is immediate because we get the value right away, which is true, right? We just return the root value and we get it. That's kind of order 1. But now we've lost our root of our tree. Right, and so we have to fix the tree because now we've got a tree that isn't a tree. It's a bunch of nodes connected and their root's gone. In order to fix this, what we do is we take a vertex from the last layer of the tree, the very bottom, the furthest bottom leaf, and move it to the top. Right? It'll obviously be higher than some of its descendants there in that second layer. So if we have some full tree here, we end up getting some node here and move it up here. But then we run the bubbling down, essentially approach, we call sifting, and basically swap it with some children. So find a child that is smaller than it and swap it to be on top. As long as that's still correct for all of the new children of that node, then the tree will be satisfying the heap property, and that new node then sifts down until it satisfies the heap property and it's greater than its parents, right? So it might end up at some other place in this leaf. But this way you make sure that you're getting something that's definitely bigger than all of them, and so we'll have to go and correct a whole bunch of edges. So again, in the worst case, it might have to go from the top all the way to the bottom, and so we'll get this log v structure. And so if we add them all up, then well, we'll get what we have down here, but I guess we have same as we had before, where we had v iterations. We have to call that delete min operation v times, and now we've got log v for this, and we're going to be doing the number of edges and vertices for the other two operations for insert and decrease key, and they're also log v. Everything's log v now. And so our final runtime is just going to be log v times that, right? Because this one's going to dominate. So we'll kind of get rid of this one. And so that's as close as like you get to kind of like n log n but where n is all of the information that describes the graph. So there's a whole bunch of other interesting properties and algorithms and efficiencies in this area that you can look into. Building the tree, there's more efficient ways to even do it than this, kind of doing multiple inserts. So heapify algorithm that can do it in a faster way. But this isn't really what's slowing down Dijkstra at this point. And there's an even faster algorithm called a Fibonacci heap, using our idea from earlier in the course that we're not going to cover, but we can talk about it if people are interested, where instead of it being, what is it, v plus e log v, we've got v log v plus e, which is good because you've got this constant just being the v, and now you're just adding the edges on the side, right? So you've reduced the factor of this log and just had another constant on it. So slightly faster. It's a very similar kind of version for the heap, but they have some more clever manipulations for updating the tree. So that's Dijkstra's algorithm. And after this, we'll go on to other path planning approaches, and so what to do if you have negative edges and other exciting tales.